everybody, welcome back. Stereopolice. I believe this is part 4 of understanding vacuum tubes. Let's dive right in. Welcome back. Thanks for being with me. Today we're going to move on from the diode to the triode. And we're fast approaching getting into some of the the plate characteristics of the triode that we're ultimately going to need to build our single-ended vacuum tube amplifier, Class A. But as always, we're working towards something. We're not trying to climb a mountain by taking a helicopter ride to the top. We're actually trying to climb it. So, let's begin with the triode. And as always, I have placing the emphasis of this overview on triodes and vacuum tubes as they relate to audio. And let me just say one other thing before I forget. There are a lot of figures, drawings in here that you'll see that look like this and that. This right here. This is from the Rider book that I mentioned previously. And I clip the drawings. I don't normally clip the text from the book because I think the drawings are so intuitive and so fun to look at. And I just clip them for purposes of me explaining this stuff. I'm not actually reading from the Rider book. You could do that yourself. I'm trying to impart some of my own experience, plus from not only the Rider book, of the 12 or so other vacuum tube books that I own and that I've read. The Rider book is not complete and it's old, so I try to impart things, and I use these awesome Rider figures here just to sort of inspire me to talk these up. All right. As far as audio equipment goes, there are some very common, and some of you may recognize these, some very common preamplifier triodes, especially if you like guitar amps. Most of us are familiar with the 12AX7. Some people have t-shirts, with these things on them. And the 12AX7 and the 12AU7 and AT7 are very similar tubes. Same size, very similar construction. They mostly, similar operating characteristics, they mostly differ based on this little backwards U right here is mu, Greek letter mu, 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 and it stands for the voltage gain of the tube, and that would be a voltage gain of the tube into an infinite impedance, or like an open circuit. So it's not the actual gain you will get when you are actually driving a load. That will be a little less. So these are static characteristics, not dynamic. But the differences are the gains. So we have a high gain here, a mu, a voltage gain of 100. The AU7 is the lowest gain of all of them, of 20. And there are reasons you might want these characteristics. And we'll get into that in a minute. And you have a medium gain of 60 on the 12AT7. And of course ECC, the same designations, ECC 83, ECC, those are more the international designation. And as you can see from this, and I actually, in order to conveniently get this without making a career out of it, this is actually results from Google's AI. All right, came up with some pretty good results. I forget what search term I used, but the results were good enough to put in here. And I recognize the results as being accurate and correct. So you can see that the 12AX7 with a high gain would be great for preamplifiers. And it says the most common preamp tube, and I believe it. And they're wonderful audio tubes. I have several of them in my equipment downstairs. And you have this AU7, 12AU7, it has a lower gain and often used for phase inverters and driver stages where you're not interested in gain. In fact, you might not want gain. You might want a unity gain or very little. And the AT7 falls in between. All right, and it depends on your design goals. And then you have the 6922, which is a wonderful tube. In fact, this tube is in my DAC right here. 6922 is in my Lab 12 DAC 1 reference. The ECC 88, you might recognize it more as the ECC 88. And it's another wonderful, it's used in high-end preamps, but it's another wonderful tube for voltage gain, and it says here it's also known for low noise. I can't attest to that, whether it's lower noise in the AX7 or not. I really don't know. Maybe it is. I just don't know. I'll tell you when I don't know something. Three of the greatest words in the English language. My favorite words, I don't know. Now, these are preamp tubes, and then you have triodes that are often used as power tubes. Preamp, I'm not, that looks like PVE, but it's supposed to be pre. And this is power, I'll just PWR. And the legendary 300B, old as the hills. Not even originally designed for, I forget, the original design was for the telegraph, maybe? I forget exactly. Someone could correct me on that. It wasn't even originally designed with high-end audio aficionados in the 2000s in mind. Believe me, you. But it's a directly heated triode, and it's very commonly used in single-ended amplifiers. Very low power, but those of us with tube amps don't need a lot of power because normally we have highly sensitive speakers that don't require a lot of power. It's a fantastic tube, and I will say this, it is very expensive. Very expensive, especially if you buy the Western Electric ones. And I think Western Electric was the company that originally developed these, and I think they still make them. Then you have the 2A3, that another directly heated triode. It says here often considered to have a more linear, transparent sound. I don't know. I really don't know. I'm familiar with the tube. I've never worked with it myself. I've actually designed and worked with the 300B. So easy to work with. So forgiving. And then you have the 845-211. I'm not familiar with these tubes right here. I'm just not. I've seen them around in literature and all that, but I'm just not that familiar with them. Now, I am familiar with these. Now, let's go down here. These tubes here, the EL34, love it. KT88. Okay, I've got a variation of this downstairs. The KT88, the KT120, and the KT150 are all in the same family. And the 6L6 GC, I'm familiar with all of these. They're wonderful tubes, and they're not triodes, they are pentodes. Pent means 5. So they have 5 elements in them, but they can be configured. The EL34 is a beam power tube, and I won't get into that, but they don't. That just simply means that you got your cathode in the middle, and then you normally have your plate surrounding it. But with a beam powered tube, it's a little different. And I'm just going to draw this kind of like this, where the plate is not completely surrounding it, and the electrons sort of go out in a beam like that. So that's what beam power needs. There are design reasons for that. But the KT88, anyway, all of these tubes that are pentodes can be configured or strapped in triode mode. And they can, and there are certain characteristics that people believe are better in triode mode than when configured in pentode mode. But pentode mode often produces a hell of a lot more power than triode mode, and they present with more linear characteristics, usually lower distortion. But like I mentioned in some of my videos, specifications don't always tell the story about how something is going to sound. So between my pentode KT88s downstairs, I have a switch near the transformers. I can switch between triode and pentode mode, and I often prefer the triode mode, even though the distortion, the total harmonic distortion, probably intermodulation distortion, is higher. But there's something about it, an X factor. I've given up trying to figure that out. People have tried to explain it. Second order, third order harmonic distortion. I don't know. I really don't know. Maybe it's all about happy electrons. Maybe it's about making the electrons happy. All right. So looking at a triode, if you remember from the previous, we have, this is a diode right here, and we have a cathode, and we have a plate, and a filament or a heater. And electrons are going to be, and there's an electron, a space charge right here, and when the plate becomes positive, we get a current flow like that, and it's a one direction current flow. So what we do to make a triode is we take a diode, same thing, we take a diode and we add an extra element in there called a grid, a control grid right there, and we insert it between the plate and the cathode, and it's normally close to the plate. It's much closer to the plate than it is, I'm sorry, not the plate, close to the cathode. It's much closer to the cathode than it is to the plate in physical proximity for a good reason. We'll get into that in a minute. And this is the schematic depiction of it, but in actuality, it might look something like this. There's our tube with our glass envelope. It's been evacuated. Our plate or anode is this cylindrical metal piece on the outside that's attached to one pin right there. So I'm going to draw this out. There's our one pin right there, all by itself. It's an electrode. It's an electrode. Then we have, let's look at the heater first. It's this right here is indirectly heated. So these two little wires right here, they don't depict it, but it's going to go up into a heater that's inside of the cathode for indirect heat. Okay, so we've conquered those two. And then, at least that's what I believe I'm looking at here. And then we have the cathode. I'm trying to figure this out as I look at it because I don't have a script for this. I don't script any of this stuff. If I did, it'd take forever and I wouldn't do it. So I'm guessing. Then we have a cathode. Let's figure this out. The cathode right here, which is an electrode with one connection. And this is the cathode right here. So that's going to be our connection. So we've drawn that one out. And then we have the control grid right there. And that's this dude right here. And you can see this is going to go up. And this is going to get attached to this spirally guy. That's the control grid. And normally it's like a spiral or a helix that completely surrounds the cathode. And the way we depict this surrounding, there's lots of space in between this grid for electrons to flow from the cathode out to the plate. So it's usually a little tiny piece of wire that's wound in there. So to indicate that on a schematic, we usually see dashed lines. In some of the old schematics, you'll see a control grid that looks like a resistor, like that. But it's not the best depiction of what's actually going on. Okay. Excuse me. I have allergies all year long, even in the winter. Every house I've ever been into. And I refuse to take meds. I'm not a medication guy. I don't even get the flu shot. We already talked about this. There's the old convention is the resistor looking thing, but basically the modern convention is plate, control grid, and cathode right there. All right. And the grid, as I just mentioned, normally surrounds the cathode. And this is a good depiction of the grid surrounding the cathode and a good depiction of the heater right in the middle for indirect heat. To indirectly heat that cathode, and a good depiction, of course, of the plate completely surrounded. And you can kind of see this stuff if you pick up a vacuum tube, in your hands, just look at it really closely, maybe even get a magnifying glass. You can see this stuff. You can physically see it. It's all there. If it's not, it ain't going to work. Now, we're not going to get into a whole lot of detail. It's going to be a fairly quick video today based on the time that I have, but just as a preliminary matter and as a sort of a comparison between the functions of a diode versus what the ultimate function is going to be of a triode, they're very, very different. It's amazing what a difference it makes. Let's see, who invented... So he started out with the Edison effect, and then came all the way up to, was it Lee de Forest? Okay, yeah, Fleming invented the diode, and Lee de Forest added the grid. One of the greatest inventions ever. It's just amazing. Such a simple little thing created the world of amplification. And had such an amazing impact, and not just in audio. Everything in electronics changed. Phenomenal. So just as a reminder, the diode, the main purpose that really we care about, although there are others, is rectification, taking an AC signal and converting it to DC. Rectification, not necessarily amplification. So rectification. Whereas just simply adding this control grid, we have an amplification device where a relatively small signal, an alternating current signal, when applied to the input, which the input is going to be the grid, and when we take our output, normally from the plate, it will be larger. So we've amplified it. Now by larger, I am saying larger in voltage. But through this process, and I'm going to get to this in the slide in a minute, we are not only amplifying voltage, we could be amplifying current, and we could be amplifying power as well. So it's just taking a small signal and making it larger, and hopefully making it larger in a faithful way. In other words, not adding too much distortion to it. You wouldn't want to have this beautiful sine wave and then coming out of this, have this weird, lumpy, or a triangle, coming out with a square wave. No, you don't want that stuff. You want it faithful, low distortion, and you don't want a lot of noise. you want to have it low noise. And a triode can do all of this stuff if the design is proper. So, in sum, the grid or the control grid, and we normally just say the grid, but it is a control grid. It controls the flow of electrons. Normally it's not always depicted this way, but normally in reality, physically, it is much closer to the cathode than it is to the plate, for a good reason. And this grid right here, and we're going to get to this in a minute, is going to be negatively charged relative to the cathode, whereas we know that the plate is very positively charged relative to the cathode. And this negative charge right here, we've got the space charge of electrons. This negative charge will serve to repel back some of these electrons. Okay, in the diode, these electrons just wanted to flow over to the plate. But now we have a device that's negatively charged here that wants to repel them back. And by controlling this voltage right here in an AC manner, we can either, I'm going to get to this in a minute, we can either repel more or repel less, either increasing the current or decreasing the current. And that's, again, I don't really read my own slides, I just put it into my own words, but that's what's going on here. Now, another thing to keep in mind, and we're just in the preliminary stages of understanding the triode. I believe in really getting into the nuts and bolts of this, because this is the last time we're going to do it. We're not going to get into the pentode at all. I'll leave that for you. We're just going to, because once you have an understanding of the triode, everything really falls neatly into place. Okay. So if you remember, let's go back to the diode for a minute, cathode and plate. It's really hard to say, what's input and what's output, relatively speaking. But if you remember back to our, let me draw this in reverse, plate and cathode. In our rectifier circuit, we would normally take the AC coming in and apply it to our plate, and the output would come from the cathode, and we get that little hump like that. If you want to call the plate would, in a diode, the plate would normally be sort of what we'd call the input, and we'd draw tap the cathode for the output. Not the case anymore with the triode. Okay, with a triode, our input voltage is going to be on the grid. I'm going to call this ground. Everything is relative to some sort of a ground reference. Whether the ground is a ground or whether it's a floating ground, you have to have a reference voltage for the whole circuit to operate on, to create paths back. A path for electrons. Circuit means circular. So any input voltage to this circuit here for this amplifier, this is not a practical amplifier, this is just a schematic here, but the input is going to be applied to the control grid. You can think input applied to control right here. So if we had some sort of a sinusoidal input, it would be applied to the control grid. And the output would be taken from the plate. And this is the same depiction, it just depicts some resistors or some loads in there, something a bit more practical, but same thing. Input applied to the control grid. This input would come from a previous stage, maybe with a capacitor there to block previous DC, but a capacitor is actually, in most circuits, is a short circuit to AC, but it blocks DC. And then we take our output, and this output could be a resistive load, or it could be an inductor, a transformer that goes to, I will draw a speaker like that. So that's a difference between diodes and triodes. Now let's look at the operating voltages in order to get, and we're just taking baby steps here to get to a point, and it's just really worth doing this. But this is a critical diagram and a critical principle, if you will, of the operation of a triode. Now here you see a triode. We have a cathode, we have a grid, and we have a plate. And we have a filament or a heater. And in practical circuits, for an indirect heater, the heater has its own power supply designated by A. And these letters are actually used, or they used to be used, and they still are to some extent, to designate different power supplies on a schematic, the A, B, and C power supplies. So the power supply A heats the filament, and that's all it does. That's its job in life. It doesn't care about anything else. Power supply B is the plate supply. So its job is to provide some very large voltage, could be, hundreds of volts, 300 upward to 900, sometimes more. But we won't get into absolute values here. So now I'm going to call this ground. This is our circuit ground. This is our ultimate reference point. Now, the kicker here, the big thing in here, I just mentioned this, and eventually we're going to call this a bias point. In order to get this tube to function properly, it needs to be biased by another power supply or a technique in the circuit. So I'll just put it like that. It can be either a power supply or a technique. So we'll call this power supply C, or a technique that places a negative voltage on the grid. Not a huge one. It could be, well, I won't get into that, but it places a negative voltage on the grid relative to the cathode. So the grid must be negative relative to the cathode. So when this is at ground typically designates 0 volts. So let's say the cathode is at 0 volts. So if we go to 0 volts, we step it up by B. So this is at positive B volts relative to the cathode. Let's go back to the control grid. This is actually, you can see this, if this power supply, if we put the positive side at ground, that means this cathode has a negative or a lower voltage, lower than 0. So it's negative relative to the cathode. That is bias. It's called bias. We're biasing the tube. That's one of the things we're going to do when we design a tube amp. We need to pick a bias point, and that's critical. That's going to be critical to the linearity of the tube, critical to ensuring that it doesn't exceed its operating parameters, such as power, and many other things. But the key thing here is just to look at these voltages and how they're arranged relative to each other. Plate is positive. And also, I didn't mention, but the plate is going to be, of course, plate is positive relative to the cathode, the plate, of course, is going to be positive relative to the grid. All right. Let me take a quick break right here. I'll be right back. Alright, I had to check on something. I heard a noise. Alright. We've already covered this. See, I've already talked this up, so there's nothing here that's new. I've covered everything on this. Bias. I've covered the word bias. And normally in an operational tube amplifier, let me just say this. The plate voltage is normally fixed. That's the power supply voltage. It's DC. It's not going to change. The filament voltage, the heater voltage, is fixed. It could be AC or DC, but it's not going to change. It's not going to vary. It's fixed. Normally our bias is fixed. It's fixed. And the only thing that's going to change is when we put an AC signal, our audio signal on here. And that's going to ride on top the bias. And because remember, in a wire, let me just draw a wire right here. This is a wire, copper wire. And let me draw a x-axis here is time. The y-axis, the ordinate, is going to be voltage. So this is actually good information. So we have 0 here, and then we have negative volts down here. So what we're doing with a bias down here is we're going negative. Okay, this is all going to be relative to the cathode. So we put this fixed DC bias down here. I'm going to put in negative 20 volts, and that could be realistic. Could be realistic. So right now our grid, right here, our grid is negative 20 volts relative to the cathode. And it's DC, meaning it doesn't change with time. So we have a bias. Now we come along and add an AC signal. And this is our audio signal right here. And interestingly, with a copper wire, you can have 2 signals on the wire at exactly the same time, and they don't care about each other. They're not going to interfere with each other, in layman's terms. And what I mean by that is once I add this audio signal, it's also going to, the current will fluctuate on this wire, but it's going to ride on the bias. So it's going to go like, it's going to ride on the bias like this. So the bias becomes the AC's 0 point. So when this AC goes positive, it's really going less negative. You see what I mean? It's going less negative, and we reach this peak here, and now it's going more negative down to the bias point. Now it's going more negative to where it reaches its most negative point. Now it's going more positive, back to 0, more positive to its most positive point. So our bias just pushes that down. And the ultimate point, as you're going to see, is we really don't want in vacuum tubes, unless it's a specialized circuit with a specialized tube, we do not want the signal on the grid to ever go positive relative to the cathode. I'd mentioned this a while back, and very briefly, and I'll say the reason why is we don't want to create, we want this cathode to repel electrons. And once this grid goes positive, we're going to create a path, a circuit. And you're going to have what's called grid current. And these grids are not adapted for a current. They will burn up real quickly. They're just not meant for that. They're very delicate, very fine wire, and they're just not meant for a current to flow through them. So we have this bias, so we push the whole grid down to negative such that the ultimate oscillating signal, that's our audio wave, will swing on that negative bias, plus and minus, but ultimately nothing is ever going to exceed zero and go positive relative to the cathode. If you need to go back and listen to that again, it's critical. We're kind of going to discuss it a little bit more in a minute. All right. Some more really fun pictures from the Rider book. So we're going to kind of backtrack here. All right. What we're showing here is a depiction of a negative bias. I always like to draw ground somewhere. So once again, our plate is very, very positive relative to the cathode. Okay, our cathode in this depiction is going to be at 0 volts. Our plate's going to be, I'll just pick 500 volts, positive. And our cathode, I'm just going to pick negative 20 volts. Negative 20 volts right there. Just random numbers, but realistic though. Now when that happens, if you remember, we have a space charge in here. All these electrons, it's our reservoir of electrons that are just floating around in space near the cathode, and they're ready to be pulled to the plate. In fact, if this was a diode, they may be pulled to the plate, ready to roll, because there's this huge plate voltage. They'd be pulled to the plate by virtue of an electric field and the forces created by that field. However, we now have a negative 20 volts on this grid. And these arrows here are indicating a repulsive force going out in both directions around this grid. And these are indicated as dots right here because if you remember, our grid is a kind of a spiral, and if you sort of cut that in half and look in this direction, you'll just see dots where the wires are. So we're looking at cross sections of the wire right there. All right. But this, you can also know that this grid is a helix or a spiral of wires. But it creates this field of repulsion relative to, this is a negative charge, so it creates this field of repulsion relative to electrons, because electrons are negatively charged. This grid is negative, electrons are negative, like charges will repel. So what we're doing with this bias is, whereas these electrons from our reservoir would normally be attracted to the plate, we are pushing them back towards the cathode via an electric field and the forces created by that field, the forces of repulsion. It's an actual physical force. It's a field force, but it's a physical force, not a touching force. But it's a physical force. In fact, I would get on a tangent and I'll tell you there's no such thing as a touching force. When you touch something, you're never touching anything. I'll leave it at that. You're never, ever touching anything. The force of repulsion you're feeling when you push on an object is you're never actually physically touching the object. It's the same kind of forces. It's field forces. But it's very interesting, but I won't get into that. You're getting very close to the object, but on a atomic level, you're never touching it. And the strong nuclear forces are the strongest. Okay. So we got this repulsion, negative charge, pushing these electrons back. And that's what's being depicted right here because of this negative bias right here. Now right here we're talking about DC, not AC. We haven't introduced the signal yet. This is just DC, and we're biasing our vacuum, our triode. Why did I put this one here? Negative bias. Okay. Oh, because of grid current. Okay. So this is the same thing as what we're looking at here, just a little more of a close-up. We have a negative bias right here. Don't need to worry about the plate. The point behind this depiction is that we have a negative bias here. And we have this repulsion that's pushing these electrons back. But every now and then, there are some electrons that will get through and try to make their way to the plate. A certain percentage of them. Unless the negative bias is so high as to stop all of them. Okay, but that's not the case here. So some will get through, and that's how we control things. Some will get through, and every now and then some of these electrons are going to actually strike the wire of the grid. And they will enter that wire. And here's one of them, and I'm not sure if he's happy about it or not, but he has entered the wire of the grid, and he will flow back in this, right there, he will flow back. So there is a very, very small current flowing through the grid circuit when we're negatively biased. We can normally almost ignore it. However, it's there and we need to deal with it in practical circuits. So let me just draw a practical circuit real quick. Cathode, filament heater, grid, and plate. So what would normally happen is we have to add some resistor here, and it could be very high, like a mega ohm, back down to ground, to channel off that flow of electrons and send them somewhere. Otherwise, they will build up on the grid, and we don't want that. So there is a resistor here that facilitates that. Called a grid leak resistor. Leak resistor. Right there. And that resistor would be somewhere in this vicinity right there. A leak resistor. The grid is leaking. Now, let's go to the unrealistic scenario. You can see we've biased our grid positive, not negative. So now our grid is positive. Unrealistic. There are scenarios and tubes and circuits designed for the grid to go slightly positive, not too positive. Not really in audio. And it gets very non-linear when that happens. But let's cover this very briefly. If the grid becomes positive, then all of a sudden these electrons are attracted to the grid wires and they want to flow. And look at all these happy guys. They want to flow. Right here. And that creates a very large grid current. Normally that is discouraged. We don't want that. Let's look at another scenario. Here's ground. We're going to call that 0 volts. We don't have a bias at all. We are keeping the grid at exactly the same potential or voltage as the cathode. Now in that scenario, we're going to have a few electrons that, because in this case, the grid has little control. Okay, it's not negative. The grid is no longer negative compared to the cathode, so it's not really repelling anything anymore. So we are going to have a lot of these little guys heading towards the plate. Plate's out here, and it's positive. And some of these electrons are going to hit the cathode wires, and they're going to want to flow somewhere. And they will, of course, flow back down to ground. So with no bias, we're going to have a little bit of a grid current. But normally we want a negative bias here. We really got to control that grid current. We don't want any or very little of it. And just as a matter of curiosity, because this is not used in audio, something called a floating grid, where the grid is not hooked up to anything. And what you're creating here is, quite frankly, a capacitor, and I won't get into that. So these electrons are going to, with a floating grid, just like in this scenario where there's no bias applied, these electrons, some of them will enter the grid, but they have nowhere to go. Okay, this is floating. Here, in this scenario, they at least have a path back down to ground, so they can disappear and go back to ground and be happy. In this scenario, they have nowhere to go. So negative charge, negative, negative, is going to be built up like on a capacitor, sort of. And what will ultimately happen when negative charge gets built up, the grid will become negative and it'll become repulsive again. But this is not practical. We have little to no control over what's going on here, and we want to control things in electronics. We don't want to be out of control. So this is not practical. We don't want a floating grid. All right. Let me see how many more slides we have. Let me just draw a circle. So 1, 2, 3. That's it. 3 more. Okay. These are fun photos, and this is just, I love these, not photos, drawings. These are, someone hand drew these things, I think. I don't know if Ryder did it himself or he had an artist do it, but this is depicting right here, and they're not showing the plate, but it would be out here like that. This is depicting a negative bias, like we talked about, like what we want, a negative bias, and this is showing how the negative bias, and this is the grid right here, and it's shown as a sort of a lattice structure. Some grids are actually, some grids are helical. Some grids really are a lattice structure. Physically speaking, they are. So it's showing that the grid being biased negatively is having a repulsion back, so it's pushing some of these back, but yet some of these electrons, based on their energy, their kinetic energy, and their velocity, are able to escape, go through the lattice, and head happily on their way to the plate, because the sign tells them where to go. They need that sign right there, the plate. Go this way. Remember, the plate directs and collects electrons. Directs and collects. Directs by virtue of the electric field, and collects them and sends them on their way back to the power source. All right, but the point behind this depiction is this. By virtue of this repulsion right here, we're slowing down the current. We're reducing the current that would normally exist. And if you remember back when we were talking about the diode, we draw a diode here. We said that for a specific plate voltage, the diode acted like a resistor, like 500 ohms or something like that, 500 ohms. And, you know, the higher the plate voltage, that resistance went down. But, again, there's something called plate resistance, RP, and in a diode, it varied depending on plate voltage. So this vacuum tube is acting like a resistor, and when we have a negative bias, this resistance, okay, when we introduce a grid and we have a negative bias and we start repelling these back, thus reducing the flow of current, this resistor is going to go up. So when we have a negative bias right here on the grid, this vacuum tube is acting like a fairly large resistance. Fairly large resistor. We don't need to get into absolute values right now. It's just acting like a large resistor. Larger than it would be if the grid did not exist. So let me draw it two ways. In this circuit right here with a negative bias, right here where we're repelling electrons, we have a large resistor. And let me just say it's, I'm going to make it up. Let me say 1K ohm. 1K ohm. And then let's say we just remove the grid altogether. Gone. Take it out and convert this back to a diode. Then the resistance between the cathode and the plate would go down to like 400 ohms. All right. So our grid is serving to increase the resistance or decrease it depending on what kind of signal we put on it. And we'll talk more about that later. So this is a key or a critical factor here in how triodes work. Now, this is unrealistic. I wish you would have drawn this in a different way, and I'll tell you what I mean by that in a minute. But this is the opposite, where we place a unrealistic positive voltage on the grid. I wish this would have been depicted as, instead of a positive voltage, a less negative voltage than was up here. Less negative. Still negative, but less negative. That would have been a better way to do it, but to me, but let's go with positive. And I want you to pretend in your mind that this positive is really just means less negative. So let's just say that this was negative 20 volts. Negative 20 volts was on the grid, and we had this 1 kilo ohm of resistance, let's say, and this is not necessarily a practical value, but it's going to be relative for instructional purposes. Now let's say over here, this is less negative, not necessarily positive. Now if it was positive, we'd have a grid current, and that's what's being depicted here, but I just don't even want to talk about grid currents because it's just not realistic. We just don't do it. So let's say it's less negative. Well, if this was less negative, then the resistor value would be lower, smaller. So instead of 1K resistance, given that this is less negative, there's less of a repulsion. based on the electric field. Lesser repulsion, more electrons coming through, meaning less resistance. So instead of 1 kiloohm of a resistor, we might drop down to 500 ohms, something like that. So by virtue of raising and lowering the voltage, the negative voltage on the cathode, we can raise and lower the resistance of the vacuum tube. And that's how the vacuum tube works. In fact, transistors work in a similar way, but on a semiconductor substrate, and the word transistor means trans, across, resistance. Transistor. All right. So just in case I didn't explain that clearly, let's just say, let me see if I can do this. Cathode voltage goes up. No, I didn't do that right. We got to go to negative values. So when the cathode voltage goes down, meaning more negative, resistance goes up. Okay? And vice versa. When the cathode voltage goes up, meaning less negative, resistance goes down. Okay? That's what I meant to say by that whole thing. It's our last slide. And this has to do with something I already covered earlier. Ultimately, I think I covered this pretty good earlier. Ultimately, the point here is we have to keep this cathode, this grid negative relative to the cathode. Even when there is an alternating current signal, such as our audio signal, even when the audio signal is on there. And so the way I described it earlier, this is our audio signal right here. And you can see that it oscillates between 0 volts, and let's just say it goes up to 1 volt, down to 0, and this is time right here. This is the time axis, and down to negative 1 volt. So if we did not have a bias, then that means if we were to place this signal right here across the grid, this grid would oscillate relative to the cathode from 1 volt to negative 1 volts. But we don't want the grid to go to 1 volt. That's positive. Then we'll get a grid current flowing. We don't want that. So what we do, we get an eraser, because this is really, really important. Kind of being redundant, but it's so important, I want to cover it. So what we do is we add a bias right here. And let's say our bias, this is 0 volts. This is time right here. Let's say our bias is negative 10 volts. So now in a resting state with no, let me get an eraser again. So critical, I think I want to cover this. So in a resting state with no AC signal, let's say there's no AC signal, right here we have negative 10 volts just sitting on the cathode, and that's what's being depicted right there. And we're happy. It's not positive, it's negative 10. We're going to have this repulsion here of electrons. So we're repelling the space charge, and then we're going to have some small current flowing. That's going to be our bias current. All right. Now, let's introduce our audio signal. Our audio signal will ride over top. These are kind of in series here. Will ride over top, not the 0 volt point anymore. it's going to ride over top. The 0 volt point, as far as our AC signal sees, is negative 10 volts. That's the baseline. So our audio signal is now going to do this. It's going to rise up 1 volt above negative 10 volts and 1 volt below negative 10 volts. So our audio signal is going to go to negative 9 volts, down to 0 over time, and then down to negative 11 volts. So now we have this audio signal that the grid will see that's going to go from negative 9 to negative 11 volts. Because of our bias, we're never going to go positive. We don't want to go positive. That's the purpose of the bias. And if you're a fan of cassette decks, I always like to add something interesting in here. And cassettes, no, I am not, but you may remember back to the days of cassettes. You would hear about bias. High bias, low bias, CrO2, FeCr cassettes, chromium dioxide cassettes, and they all required a different bias. So you had to bias the magnetic domains up from like a 0 value, let's say, for the same reason as this. Different physics, but for the same reason. It required a bias in order for the audio signal to ride on it. It's the same thing. The term bias means the same thing. Cool, huh? All right, we're done for the day. Yes, we are. I think that's enough information. I hope you enjoyed this. And I'll come back as soon as I can. And this is enough information to absorb for the tryout. I think this is more than you're going to get in most places. Yeah, that's about all I want to say. Enjoy, guys. Stereopolice. I'll talk to you real soon. Bye-bye.